Good afternoon, and welcome to this webinar, 40 is the New 20, Balancing Indoor Air Hydration to Promote Occupant Health. This event, brought to you by Engineered Systems, is sponsored by Nortec. I'm your moderator, Robert Beverly. I'm the editor of Engineered Systems. Thanks for joining us. Today's presenters are Dr. Stephanie H. Taylor. She's the CEO and founder of Taylor Healthcare Consulting, and Stephen Cutter. He's the Director of Engineering Services at Dartmouth-Hitchcock Medical Center. Dr. Taylor is currently the CEO and founder, as just said, of Taylor Healthcare Consulting, where she works to improve the safety of public and private sector buildings through a combination of research and consulting on health and productivity of occupants using principle of root cause analysis, lean strategies, and statistical analysis. With extensive experience in the medical field, numerous publications, a medical degree from Harvard Medical School, and a master's in architecture from Norwich University, she's uniquely qualified in matters of indoor air management as it pertains to health of occupants. Dr. Taylor is also a monthly columnist for us at Engineered Systems, writing about infection control and indoor air management. In his current position, Stephen is responsible for all aspects of campus facility management, as well as oversight of the in-house project design and management team at the Dartmouth-Hitchcock Medical Center. He's been in the healthcare management field for more than 40 years, and is a fellow and current faculty member for the American Society of Healthcare Engineering, or ASHRAE. He's a certified healthcare facility manager, a healthcare facilities design professional, and he's a former member of the development teams for both of those certifications. Stephen is also a voting member of ASHRAE 188 Committee, and he's a member of the 2018 Healthcare Guidelines Revisions Committee. Now, before we begin the presentation, I want to provide you with a couple of housekeeping items. On your screen, you'll see a taskbar, and each icon on the taskbar is assigned to a particular element of today's webinar. If you're unsure about what an icon does, just hover over the icon with your mouse, and a box will pop up that'll tell you the function. Please take a minute to take our survey following the webinar by clicking on that survey icon in the taskbar. You'll also see a blank questions box there that allows you to type a question in the box, and you can hit the submit button to send it to us. Later in the program, our presenters will address as many of those questions as we can. Today's event is being recorded and archived at our website. That's www.esmagazine.com. All registered participants will receive an email within 1 or 2 business days, and that will have a link you can follow to view a recording of this event whenever you like. And now I'm pleased to turn it over to today's first presenter, Dr. Stephanie Taylor.
Hello, everyone. Let's see. We're now on the second slide. I'm trying to go back to the first one. Okay, so today's webinar is essentially in 4 sections. One, why engineers and doctors need to talk to each other, and some perspectives from the field to reinforce that. And then secondly, we have some really exciting new tools that we're using to help us understand exactly what is in the environment and how those relate to our health. And thirdly, we're going to expand on some of the new data and talk about what happens indoors for both single-cell microbes and for multi-cell humans. And then lastly, some of the obstacles, benefits, and next steps to managing buildings for people. So to begin with, what do we have in common? What do engineers and physicians have in common? Well, many years of school, many late nights. We each have a technical vocabulary that excludes outsiders. I just returned from ASHRAE, and navigating the conference center is quite interesting. You need sort of an alphanumeric vocabulary. Our jobs are largely controlled by customer budgets. And lastly, what we have in common, if I can see, how did we get the last part of the slide to go? Somebody. Well, there's oh, there it is. So most importantly, both professions exist to promote and to protect human health. As a matter of fact, ASHRAE has in its mission statement that it is a global society to advance human well-being. So we have a very essential goal in common. So let's take a look at more about this. So the invisible world, sorry, I've got a bit of a lag. Winston Churchill said, "We shape our buildings, then they kill us." So that's sort of a daunting statement. Is that really true? Back from the shelters with a hole in the roof to let the smoke out, to modern buildings which keep us isolated and insulated from the outdoors. What impact are those things having on our health? So let's take a look at what is in our environment, in our indoor environment, that we can't really see with the naked eye. So this is just an animation that shows droplets traveling through the air. Here's a architect or an engineer drawing on her, probably her CAD drawings that she's annotating. And the fluorescence shows skin cells and droplets coming out of her mouth that she's putting into the environment. So as you can see from the fluorescent areas on her body, she's giving forth skin cells with organisms on them. You can see her digestive system. So all of these droplets and particulate matter that carry microbes meaning bacteria, viruses, fungal organisms, are in the air. They're landing on surfaces. They're being recirculated from the surfaces. What happens in the building, to some extent, goes outdoors. Most of it stays within the building, depending on the ventilation. But as you can see, there's a lot going on that you might not be thinking about day to day. So those of you who are listening to this webinar and you're not in healthcare, if you don't design healthcare, HVAC systems, or you're not involved in any way, don't hang up and don't leave, because the dynamics in the hospital actually exist in other buildings. So the building-occupant relationship is more extreme in a hospital because patients are more vulnerable. The pathogens are more virulent. So patients might have an intravenous line or an incision or a urinary catheter, and the pathogens might be antibiotic resistant. However, the occupant-building interaction goes on everywhere: offices, homes, schools. So with that, having said that, I'm going to turn the webinar over to Mr. Cutter, who's going to give us his very amazing experience at one of the best tertiary care health centers in the U.S., and then I'll come back again after Mr. Cutter speaks.
Thank you, Stephanie, or Dr. Taylor, and good afternoon, folks, and morning, or wherever you happen to be coming today. I wanted to talk a little bit today about the way that we design our healthcare facilities, how we operate them, and how we maintain them, or in some cases, perhaps how we don't do so well at that, how those things can have a significant impact on the health of our patients and the infection rates in our organizations. These are things we really strive to be really good at as healthcare professionals. As facility designers and managers, we recognize that we have a responsibility to create an environment within which we can provide great healthcare. And that really takes a lot. If you look at the video that Dr. Taylor just presented, organisms are everywhere. Our patients are susceptible. So to create an environment where we can practice healthcare and do it well takes a lot of work and a lot of design criteria. So I want to talk a little bit about that today. And so let's start by looking at some of the ways that we've evolved in the past. And this is a great slide. And in the mid-1800s, Florence Nightingale was very involved in thinking about how we can change how hospitals are designed. And we've been taking care of man since the beginning of mankind, or women in the beginning of time. And as the process has evolved, this was really a significant, I think, step. We started to design something called the pavilion construction. And as Florence Nightingale says well here, the essential feature is breaking up hospitals of any size into a number of detached units. And the object sought is that the atmosphere of no one pavilion or ward should escape itself into any other pavilion or ward, but should escape into the open air while its place is supplied by the purest air obtainable. Now that was really significant when you think about this is in the middle 1800s. Louis Pasteur was still in his 30s and hadn't done some of his groundbreaking work on pathogens. So it was striking that we were starting to think here about how we can change the design. A typical design, and I've got a slide here that kind of illustrates that, would be, as the previous slide said, kind of a longer, narrower building, and we would try to place the patients one on either side so that we could have a window. In this depiction, we're actually looking at how, in earlier forms, how we can manage ventilation. We recognize that the patient's respiration had an impact on its neighbors, and so there was a strong sense here that we needed to design a ventilation system. But also, in these design changes, we were thinking about staff. We were separating staff areas, sleeping areas, administrative areas to protect the patients as well. So that's just some of the earlier work when we started to recognize that how we design our healthcare facilities can really have an impact on the patients. Let's jump ahead now into the 1940s. And it was at the end of World War II, we really, the healthcare industry in this country was in pretty bad shape. Many of our hospitals were obsolete. A lot of counties had no healthcare facilities at all. And the Hill-Burton Act, let's see what we do here. The Hill-Burton Act was the government's way of infusing capital into our healthcare systems. But at the same time, they did a couple of other things. They started to develop standards, and I selected here ventilation because it's something we're talking a lot about. Is we started to see if you were going to take advantage of government monies and loans and grants, then you had to start to design your facilities in a certain way. And there was a systematic approach to how we should design facilities from a healthcare perspective. And this led to things like the Department of Health and Human Services, as Dr. Taylor mentioned earlier, the American Society of Heating, Refrigeration, Air Conditioning, ASHRAE. They've created a document on ventilation I'll talk about in a few minutes. Also, the American Society for Hospital Engineers and the Facilities Guideline Institute produced a document that's called the Facilities Guidelines for Construction of Healthcare Facilities. And that book is really designed for folks who build and design healthcare facilities and how they do that to benefit the patient in those processes. So let's step back and think about this. Some of us have heard about this process called the Infection Control Risk Assessment process. And while we tend to think that those of us that are currently in healthcare, that this is a process we use when we're renovating an existing healthcare facility, it's really a process that begins when we start to design the healthcare building itself. Assume, if you will, we've decided that this community needs to have a healthcare facility, and we're putting a team together. And one of the focuses on it is how can we build it in such a way that we can minimize the risk of transmission of infection and pathogens while we do it. And it takes everybody on the team. It certainly takes the owner's team with those who are going to take care of our patients and those who are responsible for their safety, cleaning the facility, managing the infection rates, the design team, the architects and engineers, and the folks who are building the building as well. All of these folks contribute to that process to try to make the building as best it can be. If we look at the different phases of design in a facility, the first thing we're going to think about is conceptually just what kind of a healthcare facility are we planning to build. Two contrasting, St. Jude's Research Hospital in Memphis is a specific research facility, and it's designed for specific purposes. Contrasting that, a rural critical access hospital that's small and tailors itself to community needs. Those two types of healthcare facilities are going to have much different design criteria. We're thinking about what patient populations are we going to serve, Are we going to see a population that has a high incidence of tuberculosis? And are we going to need a lot of airborne isolation infection rooms? Are we going to have a lot of immunocompromised patients? Are we going to need a lot of protective environments? We'll talk a little bit about that later. But those are the things that we think about in the conceptual design phase. Later we get into the schematic design phase where we're trying to figure out, all right, I know what the different parts and pieces of this building are. How do I arrange them in such a way to minimize the risk of infection? If I'm bringing clean instruments into a space, I don't want to design it in a way that I'm going to go right next to a dirty space on the way there is a good example. So if I have a room where I'm going to put a patient who's immunocompromised and at risk, I'm going to make sure that there are certain activities that are far away from that patient, the placement of that patient room. So these are all the kind of things we think about in schematic design. We think about the mechanical and electrical systems, ventilation systems that we're going to need to meet the needs of those patients during the schematic design. And then, not really lastly, but the last one we're going to talk about today is really what's called the design development phase. So we know what the different spaces within the complex are going to be. We know where they're located. Now we have to think about what are the surfaces and finishes and those types of things. And all of those have an impact on our efforts to mitigate the infection risks. It was interesting in my reading in history, Florence Nightingale would have said that all surfaces should be white. A lot of architects might disagree with that today, but obviously white surfaces show dirt better and it's easier to keep them clean. Simple things like that are threads that we see through the design development process. So those are just some of the things we think about as we're starting to design the building. So let's jump forward. I'm sorry, we have a poll question. And you may need to help me out with this, as I'm not sure where we go from here.
So Steve, we're going to collect that data at the end, so let's just keep moving.
Okay. So let's shift gears a little bit, and let's talk about ventilation, because that is a big piece of how we're going to protect our patients. When operating correctly, these heating, ventilation, and air conditioning systems do 5 primary functions. They filter the air that's coming into our building. We provide for temperature and humidity control to meet certain patient needs. We talk a lot about pressurization. We use that system to keep different spaces pressurized differently so that we can try and manage that flow of pathogens and dirt and all of those things that are around. And of course, we use it to bring in a percentage of outside air to keep the contaminants in the air as minimum as we can. So there's a document that's probably the standard for the design community in healthcare. It's called the ASHRAE 170. It's an ANSI and ASHI standard support as well. And it's the ventilation of healthcare facilities, how we do that. And this is really the design document that folks look to as a minimum compliance document. It will talk about filter efficiencies, how we use diffusers, and a number of other things about the types of systems that we want to see for different areas. And then particularly, we have a table that it would use that would talk about the pressurization that we require, what the air changes should be, what the total air changes should be, temperature and humidity requirements, etc. This is the document that really is the foundation for those design elements in a hospital. And this, it may be a little difficult to read, but this is a slide that's just a page taking for that. So for this is several pages of this document is like this. And for each different type of space within a hospital, we have these different design parameters. And bear in mind, these again are minimum requirements. So this table would provide us for information about what the pressure of that space should be relative to its adjacent spaces. What's the minimum number of outside air changes we should expect to see that we should design for? What's the total number of air changes? It would answer the question, should all air be exhausted directly to the outside? In other words, we don't want to reuse any of that air. Are we allowed to recirculate within a space air? What are the humidity ranges, requirements, low to min? And again, these are not specifically saying what an operating room in this case should be for relative humidity, but what the ventilation system that's to be serving an operating room should have the capacity to, what's the range that it should be able to manage humidity levels within, and the same for temperature. So for all types of different spaces within healthcare, this design document provides what those baselines should be. So let me talk about room pressurization. And as the table previously showed, there are lots of different spaces within healthcare that have distinct pressure requirements. But when we talk about patient rooms, here are the two primary types that we'll see. We'll either have rooms that are designed as neutral pressure, neither positive nor negative, for general patient population. But then we will have rooms that are positive pressure, and we call those protective environments. These are patients that will be at risk, greater risk to infections. They're neutropenic or they have depressed immune systems. And as you can see, in every space within the hospital, we will deliver air to that room, and we will be removing air from the room. In rooms where we need protective isolation, we'll be putting more air into the room than we're removing. That excess air will push itself out through the doors to the adjacent toilet room or to the corridors. And that helps ensure that, that contaminants are not going to enter those rooms. From other things that we would want to see in a protective environment room is it's a requirement of the guidelines that it's HEPA filtration, which is 99.97 efficient, highly filtered air. So all of that supply air that's delivered to the room would be highly filtered. Just opposite that, we would see a negative pressure room for airborne isolation. So there's our rooms where there's a patient, and let's say we've got a patient that has active tuberculosis, and we want to protect everyone around it from the potential of acquiring that. So in that case, we're going to remove more air from that room than we're going to supply. And the relative pressure of that room to its adjacent spaces is going to be negative. Air will flow underneath the door and from the corridor and into that, and we will not see contaminants typically go outside that. Both of these types of rooms would have pressure monitors and alarm systems on it. And in addition, in a negative pressure room, the air that's removed from that room is not to be recirculated, and in fact is exhausted at a rooftop level and away from any air intakes. So those are all design parameters that we use to minimize the risk of infection transmission and health. And where in this slide we're just using two different types of spaces, for example, we'll see the same pressure relationship in many other types of rooms. So those were just some basics of ventilation and how, from the design perspective, no matter how well a building is designed, once it's built, there really is a need for facility management teams to maintain those buildings. After it's constructed, we can design it according to the way we want it. We can build it that way. We can commission it, meaning at the day we turn it over to the owner, if you will, that it's operating correctly. But then there's a great responsibility for facility management to maintain that. There's other types of systems. Just one example here. All of the air that we're talking about passes through ductwork systems. And all of those are susceptible at some point to growth, organisms' growth. This is just one example of a maintenance method using ultraviolet light to help manage that the organisms that could be growing in there. Probably one of the other primary things we look at in ventilation systems specifically is air filtration. All of our air filters for patient care areas in clinical spaces, according to the requirements standards today, are a minimum of 90%. That's if they're installed correctly. That's pretty good filtration, and is going to keep a lot of contaminants from the outside from coming into the building. But like anything else, it's something that needs to be managed over time. A couple of examples here are just where filters can fail, and if we don't catch those, then all of those systems that we've designed to put in place won't work correctly. As filters in a system start to get built up with debris, dust, pollen, particulates, then we start to see a pressure difference across that filter. And facility managers will monitor that pressure drop to give them an idea of when they should be changing the filters. Typically we'll be changing them in the spring after the pollen season because we've gotten that last blast of contaminated outside air, dirty outside air, for instance. But that can be a little bit deceiving with the pressure drop. You don't want to rely on just that alone. Here's two examples of filter installations that are not good. In the one to your left, you can see that there's a gap between those two filter sections in the upper row. Well, it doesn't matter how good the filter is. If there's a gap where the air doesn't have to go through the filters, not only is it not filtering the air, but that's where most of the air is going to go because there's no pressure resistance through that space. On the slide on the right is an example of where if a filter starts to get too much debris loaded on it, the air pressure will just start to buckle the filter and you can have filter failure. Thinking about that pressure drop that we're managing, in both of these conditions, the pressure drop would go to near zero because the air would bypass the filters. So there's nothing better than putting your eyes on these things. But again, every hospital has these elements, and if they're not maintained well, then they're just not going to work in the way that we expect them to. Lots of things that I could talk about with ventilation. One last thing I wanted to speak to really was humidification. There's humidifying air in facilities is a challenge. In my neck of the woods, if you will, up in New Hampshire, it's pretty difficult. We go from the middle of winter when it's 10 below and there's little, if any, moisture in the air to the middle of a muggy summer where we've got 80% relative humidity outside. And we have to design and operate our system so that we maintain a consistent level of humidity within the environment. It can be difficult. Here's two slides that just kind of show the evolution of air handling unit humidification systems over time. And the slide on the right, that's a 1990 version air handling unit in a research facility that we have. And you can see how long the plumes are, how much space it physically takes for that steam to integrate itself into the airflow. Risks of trying to push too much steam into an air handling system like this, you risk condensing on surfaces. When you have warm, wet surfaces, we can get mold growth or other organisms, fungi that are growing. So we have to be really careful about how we introduce the steam into our systems. The one on the left-hand side is a much later version in one of our newer research facilities, and you can see how many more steam plumes there are, but they're very short, and they integrate themselves more fully into the air handler. This is really just speaks to the evolution of air handling systems. Not only are they more efficient, but they can be smaller in size and thus less costly. The surfaces, which this shows, if you look at the one on the right, there's a lot of galvanized material, which is not the cleanest for air distribution. The one on the right is pretty much all stainless steel. Again, the evolution of ventilation systems through the design process is what we're seeing here. So in summary, I just wanted to walk through the fact that, as a group of healthcare facility professionals, we work hard to try to build our environments to create an environment of care that helps sustain our patients and helps minimize the risk. Nonetheless, if they're not operated, first they have to be designed correctly, and then they have to be built correctly, then they have to be maintained correctly. So there's a lot of potential for problems in our buildings today. Dr. Taylor, I'll turn it back over to you.
Thank you. That was great, Mr. Cutter, and it's wonderful to get the real-world view on what's going on in hospitals. So as those of you who are still listening, Mr. Cutter has outlined a number of strategies in hospitals to help keep patients safe from infections. So now I want to talk about some new tools that we have. So if you look back in time, none of us were alive when the microscope and telescope were invented. However, when the microscope was invented, we learned that people got sick not because they had done something wrong necessarily, but because there were these single-cell organisms in our world that we couldn't see with the naked eye. So we learned about bacteria and hand washing, and then fast forward to the 1600s when the telescope was invented, we had another sort of cognitive revolution when we learned that the Earth was not the only planet in the universe. So now fast forward to this century and to a tool that I am calling the genoscope here. That's not really what it's called. But we now have DNA sequencing tools so that we can actually look at DNA fingerprints that are left in the environment. Many of you probably heard about the microbiome of the gut, so we know that the bacteria in our intestines have a lot to do with disease. They have to do with our baseline weight. They have to do with anxiety. So we're learning that our universe and our world, both in our bodies and outside of our bodies, is really populated by these bacterial, viral, and fungal communities. And most of them are good organisms, and they help us be healthy. So let's take a look at some data that we've collected using DNA sequencing tools to help us understand which indoor air parameters or spatial designs can be most closely related to whether or not patients get new infections in the hospital. So just wait for the slide to refresh. So in 2003, when our human being was fully sequenced, so if you remember in biology when the double helix DNA was unwound and all those little cross bridges were analyzed, we learned that human beings have about 20,000 genes. And this is the same as a flowering plant or the same as a mouse. So this is kind of shocking because people like to think of ourselves as being pretty sophisticated. But what we found out, that only about 30% of each of us is only 30% of us is a human being. And the other 70% in terms of cell numbers are bacteria and fungal organisms and viruses, but mostly bacteria. So each of us is like a little ecosystem walking around. Why am I telling you about this? So all of the organisms in and on our body go into the air, and organisms in buildings jump onto us. So there's an interaction between us and the buildings. And the bottom part of this slide is Jessica Green's work at the University of Oregon. And she's shown that depending on how we ventilate a building, the microbial communities will vary. So to really get a more complete understanding in a hospital about how both the architectural design and the indoor air management relates to patient outcome, we did a study. This is in a brand new, well, it was brand new at the time that the study, building was built in 2013. It was a LEED silver hospital, state-of-the-art in the Chicago area, about 180 patient beds. About 280 patient beds. Transplant unit had 10 operating rooms or thereabouts. But anyway, brand new facility. So over 12 months, we looked at indoor air conditions, and then we correlated those parameters with new patient infections. And for those of you listening, just think if you've ever had a new infection from going in the hospital, or if somebody you know has gotten an infection. But the published numbers are that about 10% of patients get an infection from the hospitalization. And those are the problems that Mr. Cutter was talking about that we try to avoid. So in this study, we had 10 patient rooms, 5 on one floor and 5 on another, with 5 of them had oncology patients. The other 5 rooms were just your general med surg patients. So they had different degrees of immunity. And we measured, just wait for my slide to come up, we measured the parameters you can see here. So in the end user space, in the patient room, we measured carbon dioxide, lux or lumen, temperature. We were able to monitor staff and visitor hand hygiene, compliance, room air changes, traffic in and out of the room, so both clinical staff and visitors. We measured indoor and outdoor relative humidity and absolute humidity, outdoor air fractions, and room pressurization. So we measured these parameters every 5 to 30 minutes. So we had about 8 million data points at the end of this study. So before we move on to the next slide, just jot down or think to yourself which of these parameters do you think was the most closely aligned in a statistical analysis with patient infections. So not to keep you in suspense for too long, we found that indoor air relative humidity was the most statistically significantly important factor associated with patient HAI, so that's healthcare associated infections. So if you look at this graph, this is pretty startling actually. On the x-axis you see the year, so it starts in the winter, goes into the summer and back to the winter. And then on the y-axis we have in red columns the number of patient infections. The blue line is the average relative humidity for all the patient rooms. So as you can see, as the relative humidity indoors approached, only went up to about 42%, the number of new patient infections fell to 0. So we were questioning, did we miss some confounding factor? Was it flu season? What was going on maybe that we were missing? So we did rigorous analysis of these data. But it held up that as the relative humidity indoors approached 42, 45%, patient infections decreased. So now this makes us, okay, now we have to stop and think. Do we really want to maintain that the only good humidifier is one that is turned off? Because these data indicate otherwise. So let's talk about why that might be the case. What's going on here? Come on, slide. So this, I'm not sure if this is going to play or not. This is a MIT study of a person sneezing, where they did strobe light analysis of the droplets that came out of a person when they coughed or sneezed. What we've discovered, this has been known and we also have new data to back it up, that we all know about sick building syndrome. What about dry building syndrome? What happens when we inhale for prolonged periods of time or are exposed to indoor air with a low relative humidity? So dry air impairs our respiratory defenses, it's harmful to our skin integrity, and we now know from numerous military studies that our brain performance and function is diminished. So for those of us sitting in a room with about 20% relative humidity, in 8 hours, even if we're just sitting, this is long before we even get thirsty, we're up to 1% dehydrated. So what does that do to us? So that's humans, and we'll talk about that in a little bit more detail. But conversely, in dry air, pathogens, meaning bacteria, viruses, and fungal organisms that actually cause disease, they love dry indoor air. They travel further. Many of them are actually more infectious in dry air. And we can clean a surface, but if there are organisms in the air that we settle on a surface or onto our hands, we might think that we're clean or that the surface is clean, but in fact it can be recontaminated. So why or how does dry indoor air help organisms travel further? So as I'm talking here right now in this webinar, I'm putting out into the environment these droplets. They're about 100 microns in diameter. And those droplets coming out of my mouth equilibrate in size depending on the dryness of the air. So if I'm talking into a really dry room, those droplets are going to shrink down to about half a micron in diameter and become what's known as a droplet nuclei. And those can float around for a very long time. That's what actually happened with the SARS epidemic. It was a dry day. The hospital pressurization was malfunctioning. A patient was sick. The organisms went out the window and traveled down a housing unit and back into residential units and infected a lot of people. So in dry air, droplets shrink, and if those droplets are carrying viruses or bacteria from someone who's sick, they go out and into the environment. In addition to the travel, there's studies that show that some viruses, not all, but some, and some bacteria are actually more infectious or more virulent in dry air. And this graph shows on the x-axis relative humidity going from dry up to 80%, and on the y-axis virus viability or infectivity. And if you follow that red line down, when you get to about 40% relative humidity, the infectivity or viability of the organisms is dramatically decreased. And then in this study, it stays low. But actually, for many viruses and bacteria, between 40 and 60% indoor relative humidity is kind of the sweet spot. That's where we are the most protected, and viruses and bacteria are the most inactivated. So to put that together, so here say you're the patient on the right in a hospital, and your sick relative comes to visit you and they cough into the environment, and say it's in the winter and it's very dry inside. The pathogens are going to come out of that person's mouth, going to be circulated in the ventilation system. They're going to be recirculated by turbulent air. Surfaces are going to be recontaminated. Conversely, if the indoor air is properly hydrated, I like to think about indoor air hydration because so many of us have bad negative connotations with the idea of humidification. So sorry about this, my slides are jumping around. It's dry in here. With balanced indoor air hydration, droplets come out of our mouth, they settle within 6 feet, and they can be cleaned. So that's what happens to the organisms. Let's talk about what happens to us in dry air. What is dry building syndrome as it relates to human beings? So unlike droplets, we can't just shrink and float around because we have a skeleton. So we have to sort of more or less stay the same size. But instead of shrinking and flying around in a droplet, our skin cracks and our respiratory surfaces become more permeable to infectious organisms. So this slide shows a person up in the upper left, and there's a blow-up image of their respiratory epithelium somewhere around their trachea. And those little green hairs are cilia, and they're constantly washing upward to keep particles out of our lungs. And you can see there's a grayish mucus layer on the respiratory epithelium, and that mucus needs to be the right viscosity in order for the cilia to work. And if that mucus becomes too thick, the little hairs cannot wash particles out of our lungs. In addition to providing a habitat for cilia, that mucus is needed for our immune cells to travel, capture infectious particles. And essentially, we need a hydrated respiratory epithelium in order to have our natural defenses. So that's one part of our body that is harmed by dry air. What about our skin? We need skin for wound healing. We need it so we don't become allergic to everything. We need it for protection and to preserve our hydration status. In dry air, as you can see here, on the left you have well-hydrated skin, and the blue lines show that our internal moisture is very carefully regulated appropriately for the temperature, whereas on the right, it shows a biopsy of dehydrated skin, and you can see that there's the upper layer, the epidermis, becomes cracked, and it's sort of a vicious cycle. We lose more internal fluid. Elderly people and very young people are especially vulnerable to dry indoor air. So when we think about nurseries or about assisted living facilities, dry indoor air is really harmful. These slides, I'm going to not spend too much time. Anyone who wants a copy of this presentation can get one afterwards. But so this, I want to talk about what happens to our brain. This is from a study that shows that at 30% relative humidity, after about 20 hours, using functional MRI imaging, your brain volume actually diminishes. And you can see in the circle that neurotransmitter activity is also diminished when your brain is dehydrated to some extent. And then on the right, we have a person who's been maintained in 50% relative humidity, and you can see their volume is more normal, and they have increased activity in their neurosynapses. So how can we take some of these things that we're seeing indoors and look to other dimensions to see what sort of confirmation we have? So this slide shows this shows the results from an area in Africa called the meningitis belt. And in this area, dry weather actually is associated with a bad bacterial meningitis, to the extent that when the relative humidity goes down, the disease rate goes up. And this is so predictable that the timing of medical supply delivery is based on the weather forecast. So we actually have known this information. We've known that 40 to 60% relative humidity is protective. This was an amazing chart that probably everyone recognizes. This is a Sterling Avondale Schofield chart from 1985 where the black bars, the black diminishing bars, show disease from bacterial infections, viral infections, allergies, ozone exposure, mites, etc. And it depicts that sweet spot from 40 to 60% where we're actually protected. So why aren't we doing this? Why don't we maintain buildings in this way? Well, there's a bit of a conflict. Hang on here. I don't know if you're seeing the same slide I'm seeing, but so building people often think, let's protect the building, and so that means we should dry the air out. Buildings don't really have cilia, they don't need hydration, whereas occupants do. So for the reasons we've just discussed, occupants do better around 40 to 60% relative humidity, and buildings don't need moisture in order to be happy, so to speak. The misnomer here is that indoor air relative humidity doesn't affect fungal growth directly. Fungi cannot extract moisture out of the air. Fungi need liquid water in the substrate in order to grow. So you might be thinking, well, it's sort of the same thing. You know, if you have condensate, you're going to take moisture from the air, it's going to condense on a cool surface, and you're going to have liquid moisture, and therefore you're going to have mold. Well, yes, in fact, that is what happens. However, the solution to that problem is not to dry the indoor air out, but the solution is to build our buildings and our envelopes in such a way that they're properly insulated. And again, I don't want to spend too much time here because I want to leave time for questions. But here on the left, we have a well-insulated building, and on the right, we have a poorly insulated building. you can see with the same indoor and outdoor temperatures, 14 degrees outdoors, 72 indoors, in a well-insulated building, you can have indoor relative humidity of 80% and you will not have a dew point within your shell. Conversely, if you have a poorly insulated building, you can dry your air out to 35% indoors and you're still going to have condensation within the wall. So the solution is, let's not dry the air out and harm people. Let's work on insulating our buildings properly. So I just want to quickly move ahead to, so a lot of times, you know, the most convincing story is a financial one. So this is that hospital I showed you the study from. They lost $15 million in 1 year due to infections that they are not reimbursed for. And if you take a look at this next slide showing a ROI analysis, and so this graph, which is impossible to read, but I just want to give you the big picture. If this hospital decreased its new infection rate by 20% with a humidification system, and this is an expensive system, it's a gas system, they would get an ROI in the first quarter of 500%. So the humidification system isn't a luxury and it's not an added expense. It actually saves the hospital a lot of money. And along those lines, what's going on with the building industry? What's going on with ASHRAE? So there are some encouraging changes. ASHRAE is beginning to incorporate the microbiome results into their standards. There's an addendum now which allows adiabatic humidification in healthcare facilities. Sloan Kettering has been an innovator in this area. And ASHRAE has ongoing research projects that are looking at occupant health and indoor conditions. So again, I just want to move through this. We have about 9 minutes for question and answer. Thank you very much. Those are myself and Mr. Cutter when we're not working. So thank you.
Thank you.
All right, thanks a lot, you guys. We've just maybe got 1 or 2 questions in, so we do have a few minutes now that the main presentation is complete. If you want to use that submission box to send a question to either or both presenters, that's it's time to do it. Andrew follows up about RH levels, asking, isn't over 60% relative humidity also dangerous? So if you want to discuss the high end a little more, feel free.
So,
this
oh,
is Steve.
go ahead, Steve.
I can talk about it from one perspective. In a cold environment, Dr. Taylor talked about condensation and building insulation. That problem amplifies the higher, if you see really high relative humidities and you don't have great insulation, you can see condensation occur. When we see condensation, especially around windows, glazing systems, metal framing, that can create moisture problems, which can be a problem. I'll let Dr. Taylor talk about it from a physiology perspective.
So 50% relative humidity is actually great for our health. If you are a primate in an NIH research lab, 50% relative humidity is their building code goal. If you're an astronaut in NASA, you'd be in 50% relative humidity in outer space. But as Mr. Cutter just said, if your building is not properly insulated, you can have substrate water, which is problematic. I wouldn't, so in terms of 50%, that's a very healthy range. 40 to 60 is really the goal. Thank you.
Okay. Daniel has a good question. Practical, day-to-day challenges. Yeah, so many maintenance departments get frustrated with maintaining humidification systems and might even turn them off. How do you overcome that tendency? How do you see facilities deal with that properly?
So I think the first step is educating people, educating facility managers in hospitals, educating the CEO, the COO. educating people about the harmful effects of dry indoor air. And then secondly, yes, humidifiers do have to be maintained. There are new ones out there where the hygienic requirements are easier to meet. The energy consumption is much lower. So how do you overcome that problem? You put in the best humidification system possible, energy efficient ones, hygienic ones, and you help people understand how essential indoor air humidification or hydration is.
Yeah, I agree with Dr. Taylor. I think sitting and listening to a presentation like this today is part of that education process. Facility managers make choices every day based on the amount of resources they have. They've got to recognize how valuable maintaining the right environment, and that's temperature and humidity. They've got to recognize how important that is and make a commitment to apply whatever resources they need to make sure those systems work. Most clinical systems are designed so that they can achieve the 40 that Dr. Taylor's been talking about. It's a matter of making sure that they're operating correctly and everything's working as it should be.
And another point about that is that in most end-user spaces in a hospital, such as the patient room, relative humidity is not actively monitored. So Steve, you can correct me if I'm wrong about your facility, but the Joint Commission only asks that certain spaces be humidified and monitored. So for example, with energy consumption, hospitals and buildings know how much energy is being used. So it's easier to focus on controlling that. So I think another very important step is that we need to actually monitor our indoor air humidity so we know where it is before we can maintain it at the best level. Thanks.
Yep, sure. Yeah. Okay, we had a question from Cindy Grant asks if you're using steam for humidification, any concerns about steam chemicals involved in the steam system, such as amines, are they problematic at all?
Any inhaled chemical, I would say, is suspect until proven otherwise. I'm not a toxicologist, so I can't talk directly about amines and pulmonary physiology, but I don't think putting chemicals into the air to be inhaled is a good idea.
And to follow on that, amines in and of themselves can be dangerous and should be avoided as they're corrosion inhibitors to maintain the piping systems and steam systems. But there are FDA-approved food-grade anti-corrosion chemicals that can be added instead to their steam systems where they're used for humidification. We maintain many research facilities, and that's an important factor at that.
Yeah. I know Sloan Kettering is having excellent results with their adiabatic system. So with the new amendment, that's another possibility for healthcare as well as other commercial buildings.
Very good, and just kind of reinforces your earlier point about training as far as whatever your particular type of system. You need to educate yourself on the specific options within that system, and might make a big difference. We're almost to the top of the hour, so I'm afraid that's going to have to conclude today's webinar. Please join me in thanking Dr. Stephanie Taylor and Mr. Stephen Cutter for their presentation, as well as our sponsor Nortec for making the event possible. If you have any additional questions or comments, please don't hesitate to contact us at webinars@bnpmedia.com. As you exit today, take a couple of minutes to complete that survey. We do strongly welcome your detailed comments to help us serve you better with these webinars. You can visit us at webinars.esmagazine.com for the archive of this presentation, as well as some other presentations and information about our upcoming events. We appreciate your time, and we hope you found this webinar to be a valuable experience. Thanks again for joining us, and have a good day.